Cybersecurity analytics. So we have Steve Reinhardt from D-Wave, who will be speaking in a minute. Before we get started, I'd like to go through the sponsors real quick to thank everyone. So Vera Technologies has been a sponsor for several years now. They're a large defense contractor, always looking for talent. ATG Eileen's here somewhere. You want to say hi?
So we're a small government contractor. We have a lot of open positions in a lot of different areas. We have some positions with Social Security that are new. So if anybody's interested, I'll be here after.
Thank you. Is anyone, oh, Ryan's here. Ryan, do you want to say hi?
Hi, Brian. I work with Clarity Business Solutions, also a small defense contractor. I will plug this time that the team that I work on actually has 3 openings. So if anyone's interested in working with me, let me know. You need a security clearance, so hit me up afterward if you're interested or know people that are interested. Software engineer, test engineer, and a sysadmin. So, yeah.
Thank you. Next Century. So Next Century is a larger company also in the defense contracting space, and actually in 2 months the speaker is going to be from their company. It's going to be on GraphQL. So if you're interested in learning about Next Century, just reach out to me and I'll introduce you. And then Areas Ventures is my company. So we have openings too, and you can work on my team with me, which is always a pleasure. Ashley gets to work with me every day, so if you would like to know how that is, you should ask her. It's a good thing, right? Yeah. All right, so next month is going to be Object Detection Workshop. So that's actually going to be a workshop, so you should bring your laptop, and we're going to go through examples of how you can do object detection with a speaker. He actually just switched companies, and I can't remember where he is, but that'll be over at the Clear Edge building over at National Business Parkway. And then in December, it'll be GraphQL. So the speaker will be discussing how GraphQL is better than the rest, and that will be at Loyola in Columbia. And then there is a newsletter that I've been trying to add more and more content to. So if you go to dataworksmd.org, there's a sign up, and I usually send out information about the next events or interesting local news topics or opportunities, or and that could be a job opportunity or just something on the side that people are looking for help with. So I would recommend you sign up for that. All sponsors are always hiring. I think everyone said they're hiring. So if you know anyone or if you're interested, either reach out to me or reach out to the people directly that stood up. And if you have any comments or questions, please email info@dataworksmd.org and I will respond. And I will hand it over to Steve. For questions, we're okay with some questions, but just be mindful of the time, and we'll go with that.
Oh, can people hear me okay?
Yeah.
You in the back? Great. Never been criticized for not being heard, even by my siblings. Thank you for having me here. I'm Steve Reinhardt. I work for D-Wave Systems, as Jason said. And so I worked at Cray Research and SCI for 1 million years, and then about 2003, I got connected with graph analytics. And I've been kind of doing that off and on for several years. And actually I worked with Aaron at York Data doing graph analytics in service of cybersecurity. And I came to D-Wave partly because Bill Blake, who some of you will remember, had just joined D-Wave. And he said, you know, there's really a lot of graphs in this quantum system here. You would really enjoy this. And so one thing led to another, and I joined. A couple years went by, and I was learning the processor, and I didn't really have a chance to go back and look at what we could do, what our processor could do in a cyber context. But I finally had time, and this is kind of the outcome of that. So last January of this year, I went to FlowCon, which some of you will be familiar with. It's a DoD-focused cybersecurity data analytics conference. And some former colleagues and some contacts of theirs and I got talking, and one of those is the anonymous collaborator that I have referred to here, and I do this mainly not to be obscure or you know, whatever, but because there's somebody who's actually been working with me on this. You know, she knows things I don't know. She is much more of a cyber person. You know, my cyber knowledge is fairly thin, hers is deep. And for, you know, she's not allowed to acknowledge that we're collaborating, so, you know, at some point I'm guessing that we'll be able to talk about that, but today isn't that day. So we have this going. It's work in progress, but that's what I want to talk about. So kind of to summarize, so we implemented a compute-intense graph kernel that finds lateral movement-like behavior, notice the word like, in NetFlow data, and can execute a substantial portion of that workflow in a quantum mode. So I'm going to talk about the remaining work we have to deliver the differentiated performance from graph kernels like the one we used. And we believe this enables a valuable new set of tools in the not too distant future. So here's roughly what I'm going to talk about. So detecting lateral movement via maximum independent set, that's the graph kernel I've been referring to. Achieving high performance with graph kernels on a D-Wave system. And then some implications for cyber and other types of analysis. So, detecting lateral movement. So, some of this I already said. Sue Nizuski and colleagues at Los Alamos. So, Los Alamos was our third customer. They have a system since 2016. And almost immediately after they got their system, Sue and company put out this paper about graph partitioning, which is, so just a question. How many graph geeks in the crowd here? Graph analysis? Okay, good. Graph partitioning, is one of the classical graph problems. And Sue and company had really done some what I thought was some interesting work. And their results were even more interesting. What they said sometimes yields better answers than the classical counterparts. So they're comparing a kind of standard formulation for a D-Wave system against the classical purpose-built graph partitioners like Metis and Kahip. And sometimes they're getting better answers, which is, and this is a generation ago on a 1,000-qubit system. So that was really intriguing to me. One of my D-Wave colleagues, Alex Condello, a year ago, more than a year ago now, so many of you will be familiar with the Network X graph analytic package from Los Alamos. And what Alex did was take a small set of the compute-intense kernels and implement it so that you could execute them on a D-Wave system. So you still call them from Python, very similar to the way you would in the vanilla Network X. But if you turn the right knobs before you call it, it'll use what we call the QPU, the quantum processing unit, instead of a CPU or GPU. And with my graph analysis background, I thought that was a really cool idea. And for two reasons. Number one, graphs are cool. Number two, many of the other interfaces to D-Wave systems require you to know a ton of stuff about the processor and more details than you would ever think you would want to know to run a computer program. And this avoids that. If you've been using Network X, you can use this. So, very small learning curve. And so, with these compute-intense graph kernels, these are the ones where the computation grows exponentially with problem size. So in the cyber world, people wouldn't even think about using it. You'd be out of your mind to contemplate. You'd be, laughed out of the place if you thought about using these on a classical system. So it got me to thinking about, for what cyber problems are these kernels or similar kernels useful? And so I talked with some colleagues, I talked with my collaborator and some of her colleagues, and we realized that, lateral movement is a big deal. And some of you may have a cyber background, but this is the point at which a bad guy has gotten into your system, and they are trying to figure out, well, what's here? And so let's kind of scout around. Let's go. The term lateral means sideways. So they're already inside your enterprise network, and they're going sideways to find out what's there. That's hence the term lateral. And that's a big problem. There was the Sony invasion that was obviously from lateral movement. There have been several of them. It's a big concern, not only in the IC, but also in banks. People are really concerned about exfiltration of all kinds of data. So we thought, okay, lateral movement. Okay, that's an important problem. So what could we do relevant to that? So think about the graph of point-to-point logins. So SSH, remote desktop protocol in the Windows context. So what if we calculate maximum independent set, i.e. the largest set of non-adjacent vertices, and as point-to-point logins explore more of the enterprise network, MIS should shrink. So that should be a direct connection with lateral movement. So that's what we explored. This is work in progress. So as of today, we've confirmed this this does what we expect on data that is not known to contain lateral movement. And we're working to confirm on traffic that is known to have lateral movement. So maximum independent set. Again, you graph geeks can check your email for a second, but for those of you who need a bit of a refresher, an independent set is a set of vertices, no two of which are adjacent, i.e. no two of which are connected by an edge. A maximum independent set is an independent set of largest possible size, i.e. the largest number of vertices. And I hope the blacks and the blues come out properly, but that's an example of a maximum independent set over there. So that's the problem we're setting out to solve. What we did, so LANL, Los Alamos National Lab, they have some data they collected from inside their own internet, or their intranet, I should say. It has been lobotomized in some ways for obvious reasons. There's 88 days of data. We focused on only the first 8. We're just trying to get a workflow working and kind of convince ourselves it's doing something reasonable. With my infinite wisdom, I chose a 4-day sliding time window. In the fullness of time, we might do something else. And we wanted to look at the shrinkage of maximum independent set as an indicator of lateral movement. And so what we found was, so here's the number of IP addresses in the data. And if we started out and said, okay, well, let's just run MIS on the whole thing, that doesn't work so well. So I backed up and said, okay, as it turns out, as you can see, that there aren't that many edges compared to the number of vertices. So what I did was take essentially all the clumps of vertices that had no edges coming from them, and I just collapsed them to a single vertex. So if I do that, then that's what the reduced number of IP addresses is. And if I do that, then it becomes doable. on classical. This is running on my laptop. And so the point here is, as I said here, I'm looking for a good graph size, and good is relevant to a large enterprise. I don't know exactly how big is. And it's also got to be something that is feasible to calculate in a reasonable amount of time. So I'm trying to find the intersection of those two sets. What I realized here is part of this is not just the number of IP addresses, number of edges and the number of IP addresses both play into this. And this isn't, I've realized as I've been doing this over the last week or so that there are some improvements we could make to this that we just haven't done yet. But this is where we are. And the point I think is, so I found that in, I believe it's Amazon's, in their AWS, what do they call it? Regions, locales, I forget, they have a word, something like that. They limit it to about 100,000 servers in a domain. So I thought, oh, okay, this is order of 100,000. Maybe in practice, kind of that's what people do. I don't know, but I was guessing maybe. And so I'm just trying to find a size that would matter to people who do this in earnest. Okay, and then I also looked at some bigger data sizes, and depending on how much I reduce things, some of those could be reasonable things. So it's not just the number of IP addresses. It's some combination of those two things. I think I already said that. So, something I want to point out is these are all running classically. As it turns out,
Sorry,
question?
This is not my domain, so I just appreciate a little clarity. When you have the point-to-point pairs, this is line 3, the 1474. It's consistent with the top two, but the maximum independent size is some scalar larger than that. Could you just explain, I guess,
Right.
the connection between the two?
So point-to-point pairs is, for graph geeks, that's just the number of edges.
Okay.
And MIS size, you'll see this, maybe I'll go forward to this slide for a second. Because this, I'm actually going to claim that this tells you something. And what it tells you is that many of these vertices aren't connected to anything.
Mm-hmm.
And you can actually see that here. So the number of edges is, what 1,400 or 1,500 or 1,200. But the number of vertices is 21,000 or 84,000. So that says most of the edges are just singletons. They're just not connected to anything.
Right. Okay.
And so, in a sense, that's not very interesting. So, does that answer your question?
Yeah.
Okay. Okay. So I thought something I've learned from my time doing cybersecurity stuff is that people doing this for a living, they have great intuition about what's going on in their networks and what they see or don't see, and presenting the data in the context, kind of in a visual way, such that they can use their intuition easily, is high value. So I wanted to convey data in a graph sense. This is pretty horrible graph visualization. This is not my specialty. But the thing I wanted to point out is that many of these, so the XXXX, those are the ones that I collapsed. And the point is that they're not connected to anything. So removing those would be something that would be an obvious next step. Okay, so a couple thoughts about this. So number one, so why not just use connected components, which is, you know, I don't know, it's literally linear in the number of edges, but it's probably order of magnitude that. And you know, I think that is reason. In some cases, that's a reasonable suggestion. The thing that it doesn't give, to my way of thinking, again, not really a cyber analyst, the thing that so if you had, this is built on point-to-point. So imagine that you had some way of using HTTP, for instance, in a nefarious way to get other connections. So if you were alternating SSH and HTTP, and you looked at connected components, you'd get completely unconnected. But if you looked at it with MIS, you'd get a different picture. So I think there is intuitively a how close is it to connected that I think MIS gives you that I don't think connected components does. You know, real cyber analysts might contest that, and I could easily be wrong. The other thing I want to point out is we need to find kind of what I call Goldilocks sized graphs. So if a graph is too small, it runs fast enough classically, and why do you need a quantum computer? And that might be great from an analytic point of view, don't get me wrong. If that's great analytically, use it and have a nice day. If the problem is too big, the data is too big, even with kind of the medium scale quantum systems we have now, you know, an exponential algorithm is still going to be infeasible. And by this I mean, so if our QPU solves 10% of a problem, then combining those 10% in 2 to the 10th different ways is something that you could imagine doing. I mean, that's 1,000, but that's not a bazillion. Whereas if the QPU solves 1% of the problem, then it's a bazillion. And realistically, there's no way to combine those partial results. So that kind of what led me down to the, you know, how much should I be reducing the graph? How should I be playing around with that? This is, I don't claim to have any answers there, just a task that needs to be accomplished. Okay, next steps, as you know, is we need to verify this on data that's known to have lateral movement. We need to find scale-appropriate visualization that illustrates the growth of connectedness, i.e. the shrinkage of MIS, from the point of view of a cyber analyst. My collaborator and I are sharing this data on a private GitHub repository, so it's Python like NetworkX is. Not necessarily the world's most beautiful Python, but it's reasonable. And we're looking for collaborators, especially those with data, especially those who might be interested in you know, downloading this kind of code and trying something. So that is the end of this section. If there are questions about points here, maybe I'll pause for a second. Yes?
How are you computing like the distance between the points? Like how are you determining like closeness?
So in this case, things are either connected or they're not.
Okay.
So distance is unit.
Okay. But it's not like you like logged in. You know, like you're talking like across the network. Like think of like I don't know, like IBM, since they just bought Red Hat, right? So they, you know, IBM's all around the world. There's no way to compute that like I logged in someplace from like California versus like New York, you know?
No, there's not.
Okay.
And so that could be, so in a flat network, you could log in from anywhere to anywhere. There are networks where you'd have, if you were in, you know, IBM, I'm making this up, I don't know anything about IBM's network topology, but if you were in IBM Tokyo and you said, oh, I want to log into a server in IBM New York, you'd have to log into some some connector server in Tokyo that would go, and then you'd have to log into a connector server in New York, and then to the specific server in New York, i.e. they don't want every last server in the entire network exposed to every other server in the network. And in that case, it would appear as 3 hops instead of one. It would explicitly appear as 3 hops instead of 1.
Is that considered like a factor within that close? Would that have like a higher?
No.
Like would you have more edges or something? Or?
No. Well, how would that appear? I'm not sure this is a great in this minute. That winds up configuring your network that way, kind of segments it, compartmentalizes it in a way that makes some of these intrusions more difficult. And so, and I guess another way to say it is it exposes the fact that you're going a long distance in a different way by the fact that you actually have to make 3 hops instead of 1. Other questions on this section before I go forward? Okay. So, graph kernels. Well, let's stipulate that those are a good thing. And how can we get good performance from a graph kernel on a D-Wave system? So, I'm going to take a step back. So, how many of you have run on a quantum computer? Okay, John. Okay, so I was guessing this might be the case. And so I was going to step back and just kind of talk for a minute about quantum computers. And the reason is there are 2 main paths, what in the classical world we might call architectures for quantum computing. One is what's known as the gate model or a circuit model sometimes architecture. This was David Deutsch started some really had a major contribution in '85. Some of the key algorithms like Shor's algorithm, which is the one for integer factorization, which everyone gets excited about decrypting things. That was defined in the '90s. John Preskill of Caltech illuminated a major issue of error correction in '98. And the current best thinking about that is it's believed to require 100 to 1,000 physical qubits per logical qubit to be able to execute in a practically reliable way. I should be clear here that the Microsoft Topological architecture is explicitly able to avoid this error correction issue. They have the other minor problem that their system is based on particles that have only very recently been detected for the first time. So getting to an actual engineered system could be a while. Google originally announced its bristlecone system with 72 physical qubits. They haven't really they've announced they have it and it's powered up. They haven't announced any results about its use. John Preskill again here in the last year or 2 has really, among others, has really kind of bring into question the digital nature of the gate model architecture. And when I say digital, I mean in the sense of the results are, I mean, the calculations are classical, but they come out as 0 and 1s. They are precise, maybe is a better term. And Preskill coined this term, noisy intermediate scale quantum or NISQ computers, meaning that we can't really count on them to be precise the way all of this theory expected. And so there's a whole bunch of focus now on approximate optimization algorithms using these gate model systems. And so QALA, isn't that a great pronunciation, is one of those algorithms that's currently under consideration. So Google, IBM, IonQ, Microsoft, Rigetti, and I'm probably forgetting a few other smaller ones, are all building gate model systems. The other primary architecture is what we might call an annealing-based architecture. So Nishimori-san from Tokyo Institute of Technology in 98 and Eddie Fari from MIT in 99 were the first to describe a theory about how to find low-energy states. Jordy Rose, who was one of the D-Wave founders, identified a path to build systems like this in 2004. D-Wave has delivered, starting in 2010, has delivered 4 generations of systems, the latest of which has 2,000 qubits. By contrast with the gate model systems, the academic knowledge is mostly empirical. There is some theory work, but not nearly as much. The problems that are friendly, i.e. well-structured for the D-Wave topology, can show a 1000x performance advantage over the best classical solvers. Real-world problems, rough parity. And by that I mean sometimes really parity, sometimes an order of magnitude ahead, sometimes an order of magnitude behind. And we've been delivering new system generations about roughly every 2 years that roughly double the number of qubits and improve some other things like the quality of the qubits in important ways that I'm not going to go into. So, any questions here before I go on? Yes?
So how about topological quantum computer? Is it one of these architectures?
Yes, that's when I mentioned Microsoft and they don't have the error prediction issue. They are a topological system. It is a gate model system, but is also topological. Any other questions? Okay. Some of you will have heard of Jülich. They're essentially a German national lab. Long ago they were known as KFA. And they built, and some of you will also be familiar with technology readiness levels from many government agencies here in the US. So they devised a quantum technology readiness level, and they put, as you can see, the various systems or quantum efforts on this scale. IBM and Google are here. This is their slide. And we're up here at 8. So we've scaled, completed and qualified. We're not yet exceeding the power of classical computers. So, okay, so I'm not going to go into a great deal of detail about the hardware of our system, but I think you have to have some intuition about what it does to be able to make sense of it and reason about it. So, the notion is you have an energy landscape like this, and you want to find often you'd like to find the lowest point. Sometimes you'd like to find a comprehensive view of the lowest points and the near lowest points. But this is your energy landscape. And what our processor does is give you a bunch of fairly low points in that energy landscape. I'm going to take a two-sentence digression here. Something that we, at D-Wave, we so much take for granted that we sometimes forget to say is that we expect our processors to be used in a hybrid classical quantum way for the foreseeable future. And one place where that comes in is exactly this. So, okay, I'm going to pick that sample right there, okay? So you can see that it's kind of in this valley, but it's not really very close to the bottom of the valley. And so what our processor is really good at is is giving you a point. If you think about all these things as valleys, our processor is great at giving you a comprehensive view of the lowest valleys. But it doesn't necessarily give you the lowest point in the valley. And this is a perfect example of this. This is in a valley, and actually, that's a valley that goes pretty low. But that particular point is not that low in the valley. What we find is that our processor, which has relatively low precision, that's one of the major issues why it's in the valley but not the lowest point in the valley. Well, classical processors have great precision. IEEE double precision floating point, almost every classical processor there is knows how to run that, and that works famously. So once you can get a sample pointing you to a valley, the classical processor can take you to the lowest point in that valley just by gradient descent quickly, very reliably. So there's this hybrid notion that I will probably forget to say, but remember that's there in the background. That is something we assume will be the case. So you get a whole bunch of low energy samples. Let me use that term. That's what our system does. And then obviously you want to zero in on the lowest one, and typically that requires some classical post-processing. Our quantum machine instruction, you'll hear us use the term QMI. You haven't heard me say qubit very much yet. A qubit is a quantum bit. It has the nature that not only can it be a 1 or a 0, it can be a 1 and a 0 at the same time. This is a good thing. But it participates in the annealing cycle, during which it's in a quantum state, a superposition state, for those of you who were waiting for me to use some quantum mechanics words. But at the end, it settles into one of the two classical states, 0 or 1. So a coupler is a physical device that allows one qubit to influence another qubit. A good metaphor for this notion is picking teams. So I'm a basketball player years ago. And so if you wanted to pick a team, you want to pick good players. I mean, that's obvious. But there's also the effect that you want to pick players that play well with each other. And so this is exactly that notion. So this allows, so Michael Jordan and Scottie Pippen, they played famously together. I mean, they won a slew of championships together because they played together well. So what you can do with this coupler is you can say, I prefer to have those two on the same team, if you will. You can use this instruction to pick an optimal team. On the other hand, you think about, I was also a Lakers fan. I should say am a Lakers fan because they've been pretty horrible for a few years. So you may remember when Kobe and Shaq and Karl Malone came there and Gary Payton, and it just didn't work. They had, players are great individuals, but it didn't work as a team. And so you might say there was noise about Karl Malone and Kobe Bryant didn't get along. So in that case, you might say you want to have this coupler. You want to say that I don't want those two on the same team. I don't think it's going to work. So those are the physical things. You have qubits and you have couplers. Okay? So those are in the hardware. You can't do anything about them. Just be aware that they're there. The things you can control are these B sub i's. And so these are the weights on the qubits. So what you can say is, so as I said up here, each qubit is eventually going to be a 0 or a 1. If you don't set the BII, then you're saying, I don't care whether it ends up a 0 or 1. You know, assume that it starts at 0.5 and it goes wherever the calculation takes it. That might be okay. But you might have knowledge, you might have something about the problem. You say, you know, I'd really rather this one wind up a 1, and I'd rather this one wind up a 0. So you can dial that in by the weights that you put in there. And those are on a scale of 0 to 1. Similarly, the B sub ij's are that's the Michael Jordan, Scottie Pippen is a close to 1 value, and the Karl Malone, Kobe Bryant is a close to 0 value, because you don't want those on the same team. So those are the things that you, as a programmer, in the fullness of time, these are the things that you, as a tool developer working on behalf of a programmer, will do. And so those are the B sub ii's and the B sub ij's are the things that you control to get this processor to give you the answer you want. Then the objective function, this is a real value function, is minimized during the annealing cycle. And so the Q sub i's here, these are the qubits, and they wind up in a classical 0 or 1 state at the end. So this double summation here, really it comes out to if Qi and Qj are both 1, then whatever B sub ij is preserved into the sum. Otherwise, it vanishes. So it's really, I know some people look at that and they kind of turn their heads, but it's really a very simple calculation. Another thing that I haven't said yet is that the processor is non-deterministic. And so while you can think about it as you're getting the lowest energy solution to this problem, in practice, it's actually more accurate to say that you're sampling from that probability distribution. And sometimes this seems like a pain in the neck, because if you really just want to have the lowest energy, then just give me the lowest energy for crying out loud. But there are other places where it's very interesting to know, okay, maybe you do want to know what the lowest energy is, but you also want to know how robust is that answer. Are there other solutions that are as good or almost as good? Sometimes that can be really valuable, and our processor is extremely good at that. So that is our quantum machine instruction. And at this point, I used to say our one quantum machine instruction: use it wisely. In fact, with the most recent system, we added reverse annealing, which I'm not going to go into, but it's looking extremely useful in a number of cases. And it does roughly what it sounds like. It allows you to steer annealing backwards, which can be really useful in some cases. Any questions here before I go on? Okay. So this quantum machine instruction, so computer science people talk about this as a quadratic, i.e. pairwise interactions, unconstrained, meaning in the world of constraint satisfaction, the constraints have been expressed as penalties and kind of pushed into the problem rather than being left outside the problem. So unconstrained, binary, the results are zeros or ones, optimization or QMO problem. Physicists refer to this as an Ising model, or if they know German, it's an Ising model. Operations research people refer to it as a UBQP. Some statisticians refer to it as a probabilistic graphical model. It's all the same math, just different terms. Okay, so now you have a problem and you want to map it to a D-wave system. So at a high level, what you do is, so you start out with your original form. It could be a constraint satisfaction problem, it could be a graph problem. It could be a problem that there's no straightforward way to represent, or at least an existing way to represent it as a cubo, so you have to write the cubo yourself. Any of those can happen. And so then you write a cubo, but our hardware has its peculiarities. Some people would say that's being gentle, but it does. And so typically you kind of lower it to what I call a hardware compliant cubo. And then that's executed on the QBU. You take the results back up, kind of lifting them up from the hardware to the point of solving your original problem. So some things that kind of come in are required when you're doing this. That if you haven't run a quantum computer, I almost guarantee you some of these will seem so weird you can't believe it. And I'm just going to call out some of the best known methods. So one thing is mapping to the cubo form, and actually this is a wonderful innovation of D-Wave Network X. It does this for you. You don't have to worry about it. You can just come to D-Wave Network X with a graph, and it deals with everything below here. Okay, so this is a huge win from an easy use point of view. So one thing that can happen is that when you go from an original problem to the cubo that you want to execute, that the number of variables in the problem grows substantially. There are many that you start out with n variables, you wind up with n variables in your cubo. There are one I'll show in a few minutes where you start out with n, you wind up with n squared. If I'm remembering, there are some that are worse than that. But the point is that, coming back to my Goldilocks size problem, if your problem explodes, it's just going to be too big. So you want to be careful of that. You want to be aware of what's going on there. Often you'll want to be able to reduce the cubo. So if you can find frozen variables, i.e. if you can recognize that in all of the optimal or near optimal solutions that a variable is always 1 or always 0, then you just eliminate it and you have a smaller problem to solve. Almost always, real world problems wind up being bigger than a hardware compliant cubo, and as a consequence you need to decompose, or other people use other terms, but you need to decompose the cubo into QPU sized chunks. And there have been a few different things, methods implemented there. Energy impact is one. Recombining elite solutions is another one. And I'm sure there'll be more. We're in the early days. Then once you get to the cubo, and you need to embed the logical problem into the hardware graph. So our processor has fairly sparse connections. So if you think of a simple problem, if you have a clique, a complete graph where every vertex is connected to every other vertex, that can easily have, so say that you have a clique of size 10. Well, our hardware qubits in today's generation have a degree of 6. So if you have a problem variable that has a degree of 10, that doesn't embed directly. But what you can do is you can say, oh, well, I'm going to take 2 physical qubits and I'm going to link them together in a way that makes them act in lockstep. And together, 6 plus 6 is 12. Of course, you lost 2 because they're each is losing 1 by connecting to the other. But the 2 of them together have an external degree of 10, and that matches the problem you started with. So that's what embedding does, and it can be a big problem or a little problem depending on or I should say a little task or a big task depending on the problem. Some of the best methods there, when you put together multiple physical qubits to represent a logical variable, If you get too many of those, then it gets harder and harder for them to stay consistent. Those things those collections are called chains, and so avoiding long chains is important because they tend not to stay consistent. Also, something that's kind of emerging there is
How do you avoid those chains? Now,
Excuse me?
How do you avoid those chains? The routine is going to come up with the embedding, right? So can you tell the routine come up with the short chains?
We don't have the perfect answers back yet.
Okay.
People are, so there's a couple different answers in my view. There's, one is that you think about how to represent your problem, if you can. Going back to things like reduce up here, if you can carve away some of those connections at the problem level before you ever try to embed it, that can be a huge win. And often, the problem is kind of simplistically formulated as a very dense graph, but if you think about it deeper, you can realize, oh, well, some of these cases are impossible, so I can just prune the graph at the logical level.
Can I tell the embedding routine that the maximum chain size has to be 10 or 12? Come up with an embedding with this constraint. I'm getting chains up to 17.
Right. So the answer is I'm not sure. There's a new embedder that I'm not sure whether it's already out or just about out.
Okay.
And I know that was a factor in the development of that.
You can
So-
tell. Okay. This is the maximum.
I think you can,
So
but
is there
I
an
can't swear.
attempt to minimize the length of chain?
Yes,
Yeah, of course.
yes,
Okay, well, it's successful.
right.
Yeah, definitely like to see
Well,
whether it's successful or not.
Right, successful is important to the
Right.
issue. So your attempt is to do that, but you don't necessarily.
The new embedder might be.
Right. And I know that is an effect that we know is important. And exactly how we expose it and how we satisfy it, we will be figuring out over time. But it will become more possible to do that.
That routine is available through your interface. Can I download that or what do you do that? Still in the works.
I'm not sure whether this is literally out or not. So give me,
Yeah,
send me an email,
I'll send you an
and
email.
I'll follow up. So another thing that I haven't really talked about yet is, well, I guess I did when I mentioned the fact that you want to use a classical processor and a quantum processor in a hybrid mode because the quantum processor has relatively low precision. I'm coming back to that. So, our precision is a handful of bits, 4, 5, 6. People count it different ways, but it's not 32 bits or 64 bits. And so, something people sometimes do there is they bin values into discrete ranges, and they kind of force the classical part of the solution of the code to deal with the fact that the quantum part is not high precision. But that's the reality of the processor. Okay, now once you get to the point where you have a hardware compliant QUBO and you want to execute it on a QPU and get the best results, there's a thing. So I mentioned chains. You like chains to remain valid, but the same scale that controls how you connect, the same B sub ij's that control how you connect qubits within a chain, control how you connect qubits outside of a chain. And so it's not obvious how to do that. There is a way to start with a setting that you can calculate algebraically. It's not perfect, but that is best known method. Something that you'll typically want to do at this level is sometimes there can be hardware calibration error. And so if you take part of a problem and invert it, then, and you run it both ways, you you know that it should center on 0. And so if it's a little bit off, you can subtract that out so it actually does center on 0. And so that's what reversing spins allows you to do. And the other things like, I kind of skip these. This is sort of getting into the weeds here. But my point is to kind of pop up a level about this slide. These are the things that we have to do to go from an application level statement of a problem to something that runs well on our processor. And we don't do all these things perfectly today. But I want to point out that this is a graph giving you actual evidence of what I mentioned earlier. So this is a slide showing cumulative annealing time on the x-axis on a log scale, and the fraction of valleys seen. So back to our energy landscape metaphor. This is, if you think of all the valleys, how many have been seen by this solver in how much time? So this is, in the blue here is a D wave, and here in the purple and the yellow and the red are 3 classical solvers. And you can see that the D, so if I pick here, that's halfway between 10 to the 4th and 10 to the 5th. And if I pick here as the median for the purple HFS, I'm maybe not quite up to halfway between 10 to the 7th and 10 to the 8th. So that's almost 3 orders of magnitude advantage to the quantum processor. That is a big advantage. In reality, when we start with a real world problem up here, these mapping steps lose a significant amount of performance, efficiency today. So that's something we're working on. So something else, the first thing on the prior slide was about mapping to a cubo, and that's something we want to do efficiently. And that's something that in places a program where someone mapping an application has significant control over. So this is back to maximum independent sets. I chose a graph here, and here's our objective function again. And remember, we want to choose the q sub I that minimize. Sorry, I'm wandering around so much.
It's okay.
We want to choose the q sub I that minimize this function. That's what our processor does. So if you think about this a little bit, there are 2 things that we want to balance. Number 1, we want some vertices in our maximum independent set. So there has to be a reward somehow for vertices to be in the maximum independent set. And on the other hand, there has to be a penalty that anytime 2 vertices are on our endpoints of an edge, we don't want to include that edge. We don't want to include, we don't want to include both of those vertices. So there has to be a penalty for that. So obviously, people have thought about this. I mean, here's the URL for it. I found this particular formulation. So what this says is, if I is equal to j, that is, say, if you think back to my upper triangular matrix that I showed, then it's -1. So that is a reward, since we're choosing the lowest value, the minimal value. So a -1 is a reward for a vertex just for existing, basically. And then, but if that's an edge, an existing edge, then we penalize it. And we penalize it by more than the amount that the total would be rewarded by the 2 endpoints. So if you included both endpoints, you get a -2, but if they're connected, you add a 3, so that's a +1, which is a net penalty. Okay, so you'll hear the word penalty or penalty model a lot in this context. And everywhere else, just make it 0. So actually, I realized my upper triangular matrix hasn't appeared yet, but it has now. So this is taking this graph and using this formula and coming up with this. And we often write our cubo in this form as an upper triangular matrix, mainly because this is the form that our hardware takes. There's a symmetric form that is just as reasonable, but many of us think in this form. And so this is the cubo. If you take that and you apply that, that's the cubo you come up with, and that's the cubo you could just solve. And so if you think about it, you say, well, what if I included vertices 1 and 6? 1 and 6. Oh, there's an edge. That would be a bad thing. So I say, yep, there's a 3 there. So that's a penalty. I say, okay, well, what if I included vertices 4 and 7? So there's nothing there. 4 and 7, no edge. So no penalty for that. Okay? So that's how this works. And then there's, as it turns out, a maximum independent set. There are actually a number of redundant, or a number of possible solutions here. Here's one that has, there are a number that have 6 vertices. So there are a couple things I want to point out. Number one, and probably the biggest one, is that the problem had 12 vertices, and the cubo has 12 variables. So it's scaled with n. This is a good thing. And there was another point I was going to make here that I forgot. Okay, so by contrast, let's think about mapping a traveling salesperson to a cubo for a second. Okay? So I used the same graph. I modified a little bit so that all of the vertices had at least degree 2. And we got the same problem. Here we got this piece of IJs, and how are we gonna map this? Well, I've saved you the details there because the details are pretty gross in my view. But you'll see many of the formulations used for vertex I at step k, where since you have to visit n cities, n steps. So you have vertices 1 through n at steps 1 through n, which is n squared. So that means that your cubo here is going to be giant. And so that is possible. It's something you can do. If you know n is going to be small, it might still be a reasonable thing. But in general, that's not going to be a good match for our system. I'm guessing that almost none of you have been thinking about conversions to cubo and how your expansion of variables, what your degree of expansion would be before tonight.
I have a question.
Pardon?
I have a question. For the slide, the previous slide, why was 10 a matching, why was 10 a set, a variable set? On the slide before that one. Doesn't it have an angle?
Excuse me?
10. Isn't 10, didn't you say those that are circled? Yeah, why is 10 a matching set?
Why is it in the maximum independent set?
Yes.
There is no edge.
No edge between 10 and 11.
Oh, it's okay,
Yeah,
got it.
There's none of it's adjacent.
I'm thinking
versus-
because it's okay. Nope, never mind, I see it.
Yeah, no problem.
Hey, excuse me?
Okay, so,
Steve.
oh, yeah, sorry.
I just want to clarify, so with the matrix that you wrote for Bij, so if you use like the quantum annealing computer, the Qi and Qj that you got is by minimizing the objective function, the Qij that you got is the MIS. Am I correct? So that's you're trying to. Oh, okay. So then my second question is, instead of using quantum annealing, like using a classical simulated annealing method, can it achieve the same purpose by using the same objective function?
So often it can, yes. And so I ran a lot.
Okay.
Yeah. I mean, once you have the problem, you can solve it by various methods.
Okay.
Simulated annealing is one. There are some low tree width solvers that you'll hear about that kind of mimic what our hardware does to some degree. There are taboo solvers. There are a variety of things. Monte Carlo. Yeah, Monte Carlo. Yeah.
Oh.
One quick question. On the slide previous to this, like a traveling salesman problem, is it more efficient? Like, what's the practical? Like, would you do that in a QRO form if you could? Like, is that better than? Like, is that like a more efficient algorithm to use? I'm not a quantum guy at all, so. I mean, I understand like the if you're solving this like traditionally in like a comp sci practice, like this is like a hard
Right.
expensive.
It's an hard
to
problem.
solve. Yeah.
So my point here was about the expansion of the number of variables.
Yeah.
And what that means is that it's going to, if you remember back to my point about, so our QPU at any point in time is as big as it is. And so within that, within the problem size that you can map directly to the processor,
Okay.
we know that quantum effects pertain, that we can get quantum speedups. We can do that within that size. But once we get past that size, then we're solving a this size problem and solving a this size problem here. And then we have to combine those results classically.
Okay.
So if we solve these two problems and we get a handful, say 10 results for this and 10 results for this, well, we don't know which one of the results up here might go with them. So we have to compare all those combinations.
Yeah.
That's 2 to the 10. So, did I do that right? No, that's only 2. That's only 2 squared.
Okay.
But if to go back to the numbers I used earlier, so I don't confuse myself. If we said that the whole problem was split into 10 chunks, and we wanted to recombine those, then we would have many to recombine. But it might be a manageable number. If we had if we had 100, if the whole problem had 100 sub-problems, then recombining those 100 sub-results is just a colossal number of things to recombine. So that's kind of what I was talking about, the Goldilocks size.
Sure.
You don't want to get too big. And typically what we find is that if you're up at n squared, you're too big.
Okay.
And so it's just not going to be feasible.
Thanks.
Yeah, sorry, that was a roundabout answer. Okay, so there's what I thought was some really interesting work by, again, some Los Alamos people, Shafri and Risto Gijev and others. And what they explicitly, they wrote an algorithm for the, in this case, the max clique kernel that is explicitly classical, or explicitly hibernating. And by this I mean, so CPUs and GPUs on the one hand, and QPUs on the other hand, they have very, very different natures. What are they good at and what are they bad at? Very, very different. And so what you want to do is use each for its strings. So what they did was use classical techniques like finding the k-core graph. So that's kind of cleaning away all the vertices that have degree below k. And then core halo partitioning, which is, I won't go into. They use that to partition the graph into the subgraphs that each of those will fit in the QPU, and then you find the max clique of those. And so that's a way where you use classical processing to shrink a big problem into things where the QPU can help. Of course, in this case, it's limited to finding cliques that are embeddable in the QPU, which is only of a certain size, but still. And so this is a degree of freedom that I think we're going to find really valuable because for these graph kernels, things like MIS, min-vertex cover, min-vertex coloring, etc., there are a variety of things we can do in those kernels to use the QPU effectively. Okay, so I should probably speed up here. I'm sure you're, I'm going to skip a few things here. So I also want to draw our attention forward a little bit to something we have in our heads is at the end of next year, we have a new processor coming, which is going to be substantially faster. And you know, it's always good to have fast hardware. So it's targeted at 4,000 to 5,000 qubits. Also has a denser topology. So if we look at the problem, the clique that can fit in a processor today, it's 64 variables. So 2,000 processors, 2,000 qubits, 64 variable clique will fit in. As Brad was pointing out, it does have chains that are longer than we'd like, and so they don't always stay consistent. We're leaving that aside. So we have more qubits, so that changes this, 2 to 2.5 times more. That the number of the effect it's going to have on the number of variables in the QMI is to increase that by 1.4 to 1.6. Denser topology increases that by about a factor of 2.8. We have changes coming to the annealing process and to the hardware itself, especially lower noise, which are very hard to quantify. We have better algorithms and tools, like things like embedding, that give us maybe a 30% increase in the number of variables. So you add that all together, you get a factor of 5.46 over 64, which is about 326 variables. Well, there are some problems that go from classically tractable to intractable in that difference. So we're working with some people in personalized medicine. They're using Markov networks. They're saying that we're at the 50 range today, and they're saying that a few hundred are intractable. So if we get to 326, that could be a very good story for that context. Okay, implications for cyber and other analyses. So, detecting lateral movement via MIS is only one use case. Here's the set of kernels we have implemented currently in D-Wave Network X. Something I'll point out is min-vertex cover is another of those kernels. A vertex cover is a set of vertices where every edge has at least one endpoint in the vertex cover. So every edge in the graph is touching one of the vertices in the cover. Yeah, those are two statements of the same thing. And then a minimum vertex cover is a vertex cover of smallest possible size. So you can see here some examples. This is a vertex cover. This is a min-vertex cover. Similarly, vertex cover, min-vertex cover. So some other use cases that we found were, for instance, min-vertex cover is the optimal solution for worm propagation. And so if you want to defend yourself against worm propagation, then vertex cover is a good thing to know how to calculate quickly. I'm not going to go through the rest of this. There's another area that we find very interesting, and I don't understand it that well. One of my colleagues understands it much better, and this is topological data analysis. And I think of it as a related use case because it's heavily dependent on these graph kernels or similar graph kernels. Elizabeth Munch, professor at Michigan State, who has been working on TDA for quite some time, she describes the goal of TDA as to find and quantify structure in noisy, complex data. Well, it seems like a lot of us are trying to do that these days. There's also, in particular, there's a feature of TDA that's called persistent homology. Persistent meaning it persists over some time, over some range. And it highlights the relative prominence of homological features in the data set. Here's an example. So what you do is you start with your data and you'll see that the radius are increasing. Excuse me. And what you do is you keep track of when does something become a circle, and then at what point does it get essentially filled in. So you can see here this connects, and then down here it's essentially gone away. So that's referred to as birth and death, respectively.
Is this time dependent? Do we look?
No.
What is
No.
the axis?
You're just growing those regions around every dot, right, until you get a connected region
Right.
with it.
So it's
separated.
the only thing that's changing here is the radius.
So,
The radius of the circle around the points. Okay? So what you wind up with, so this persistence diagram, and here persistence is, for how many of these radiuses did it persist? You wind up with things that are far off the diagonal, like this point up here, means this is a structure that persisted for a long period of time. And so those are things that tend to be more interesting. And this is a way of illustrating data that is somewhat data agnostic, and many people are finding interesting. So it's believed to have high analytic value. There are kernels inside it. One is Wasserstein distance, also sometimes known as earth mover distance, between two graphs. And another is min-clique cover. And it was interesting talking with Liz Munch about this. She said, well, one of the dirty little secrets, so DARPA's had two programs on this. The first one led to the IOSD, which is a fairly well-known data analysis company tool. And so persistent homology is like a next phase of TDA. And lots of excitement about it. DARPA has run programs. Other people are excited about it. But people don't use it that much. And she said, well, the dirty little secret is it's ridiculously compute intense. It's like, oh. And the compute intensity in the case of persistent homology is in this min-clique cover, which is another graph kernel. So what people do is they limit the number of dimensions, and that reduces the analytic value. So my colleague Jesse Burwald and Liz Munch and another of my colleagues, Joel Gottlieb, down here is the reference if you want to look it up. They have implemented Wasserstein distance, and they're looking at a quantum TDA package that they're thinking about how to open source. So, to my way of thinking, this is another way where these core graph kernels are going to prove to be interesting. Okay, so winding up where I started, so we implemented a compute-intense graph kernel that finds lateral movement-like behavior in net flow data and can execute quantumly in part. We have work to do to deliver differentiated performance in these graph kernels, and we believe this approach will enable a valuable new set of tools for cyber analysts. Questions? So here are some things you could, so we have a UA users group known as qubits, and here are the last several, the slides from these last several, and they're 80% of the presentation. So the one just a month ago was 2.5 days worth, and 80% of the presentations are done by non-D-Wave people, and almost all of those are about applications of the system. Questions? Yes, well, Jason, we'll get the slides out somehow.
Yeah, I'll post them and send out on next to Joe event.
Yeah. So I enjoyed your talk. Thanks, Brad. I've been curious about the D-Wave system for a while. One of the illustration slides you had at the very beginning was kind of a 2D landscape, showed optimization, and showed that the D-Wave can kind of select points. Do you know roughly, or does it make sense, like, can you tell us how many dimensions is that space? Like how many dimensions do you optimize over? And then secondly, and I think you mentioned this once, it's possible to have like very kind of non-robust minimums, and then it might be also possible to have like very robust minimum or like a very widespread minimum or value. Does the D-Wave, when it samples, is it more likely to get a robust minimum, or is there a chance it'll get a lower but possibly spikier minimum? Sorry.
You should repeat your first question.
The first question was how many dimensions does it like optimize over?
So, so I think the real answer is it depends on how many variables in the problem you embedded in the system. So if you start with a problem that is structured like our topology, on a 2,000 qubit system, it's a 2,000 dimension problem.
Okay.
Now, a 2,000 dimension problem with highly constrained connectivity. Highly constrained connectivity. At the other extreme, if it's a clique, then it's 64 dimensional. And actually, the Chapuis paper did some interesting work with taking problems that were structured like our topology and backing off a little bit. So making some chains and comparing that with classical solvers. So obviously those were artificially constructed graphs, not necessarily reflecting any problem that somebody would solve in the real world. But what they showed was that the performance benefit of was, once you get above a few hundred variables, that we were just clobbering the classical solvers. So it's if we had problems that were structured like our hardware, we'd all be millionaires. There aren't that many of those, and so mapping from the real world to those is not an easy task. Today you wind up with like 64, which is not easy for classical solvers, but is often doable for classical solvers. And like I was illustrating, if we get to the 325 range in our next generation, that's going to be a lot harder for classical solvers to manage. And we feel like there'll be a lot of times when much bigger range. That was the first part of your question.
It was.
Give me the second one.
The second part was the kind of the robustness of the minimums. Is there a way to, because often for a lot of problems, you might prefer a robust minimum over a lower but less robust minimum.
So I guess I want to clarify your question a little bit because so the Denchev paper from Google folks, this is December of, is that 2015 or 2016? One of those. It's the Denchev is the first author, and they introduced the notion of rugged energy landscapes.
Okay.
And so they're talking about, do you have valleys that are like this, or do you have valleys that are like this?
Right.
And so I think of that as an attribute of the landscape.
Mm-hmm.
And depending on how low the bottom of the valley is, you know, that tells you whether you want to sample that valley very much. So you could have a valley that's like this, that's down here, and another one that's up here. And obviously, you want to sample this one a lot more than this one.
Right.
So I'm struggling with how to respond to your question.
Well, if you had a wide valley, is the D wave? I mean, if the D wave is kind of sampling minimums or sampling points and getting a bunch of minimums, is it more likely? I don't know. Is it just kind of equally likely to sample points in the space, or is there something about the minimum that they kind of draws the sample? Yeah.
Okay, so we have demonstrated quantum tunneling in our processors. That is now accepted by the community. And what that is doing is pulling too low values.
Mm-hmm.
So if we did have this case, this one would be sampled, assuming this is kind of a relatively significant difference. This one would be sampled way more often than this one. So if there are ones like this that are all about the same, and if there's one like this that's at about the same level, then this would have probably more samples in it. But this one would have some, probably, and that can be important.
Okay.
So I hope that answers your question.
It does, yeah.
Okay. There was a question back here.
Well, I was just going to reference what he was saying there. From my experience, if you look at the probability of any particular state, it's based on e to the minus objective function value.
Mm-hmm.
Okay? What you find is the D wave lowers, find solutions as close to the lowest as possible, given the number of samples at any particular energy. So what I've seen is it easily, for the problems I've been solving, it's within 1% of some boundary that I may or may not know the boundary, because the cloud of solutions, you know, the cloud of excited states, there's a large cloud. So you may not see the actual global minimum, but you see a lot of the values close to it, we'll say. And so I don't see how you'd even see anything at, we'll say, higher local minimums, because it doesn't drive to local minimums, it drives to the global minimum. Okay, so what you see is you can find local minimums for every sample, okay, but that's not what the D-Wave would find. It finds a cloud of states that have very low energy. And the reason it doesn't always get the global minimum is because there is noise in the system, and it's going to bounce out off of the ground state, but not very far. That's the way I see it.
Other questions? Okay, thank you for your time.